Well, the start of my presentation. So I'm going to talk to you about performance of GeoJSON in the browser, and but there are more important topics in life, and so actually I'm going to talk to you about death, famine, war, taxation. No, this is a joke. I think I just I will never get the Soul Cuts award ever, but yeah. Okay, so a bit of background. I work at the University of Melbourne at the ORIM project, and we are building a system. I'm part of the e-research group, which means that we do e-science. So basically, it's IT applied to science. And we're trying to build sort of a laboratory in a browser for urban researchers, which is pretty vague because there's no such a thing as an urban researcher. But the idea is that people like epidemiologists, urban planners, traffic analysts, people share an interest in the same set of data and tools because all of them are working on the same space, like urban space, built-up areas. So, and we are building a software to do exactly this. So to provide them with data collected from various sources across Australia, and tools like R modules and Java modules and whatever. And so they can combine tools and data in the browser. They can upload data, and everything is supposed to work smoothly. Now, me personally, I had this issue because it was decided at the beginning of the project to use GeoJSON vector graphics on the client. Why? To give the best possible user experience. So you can have change color maps on the fly. You can use brushing, you can have tooltips, you can highlight, polygon stuff. Good. Problem is that you may end up with something like this. So there are 2,200 polygons across Australia for this particular statistical areas, this is just a subdivision of Australia into homogeneous statistical areas at level 2. As you may see, Australia is a big country, but all the population is here, which means that you can have polygons like these, pretty big, but pretty simple. So just a few points. At the same time, you have very small polygons, very detailed polygons, small ones. And of course, you need to find a way to have all those polygons sent to the browser in an efficient manner. So this is the problem statement. Now, being a statistician by training, I wanted to build a model of this. So I start thinking about what the factors affecting performance could be. Rather, the factors affecting performance that I could control. So there were, of course, the size of response in bytes, which is, I suppose it was one of the most important things, but it's one of the factors. The server DBMS performance, of course. The protocol used. Actually, we were forced to use HTTPS for some reasons, but I really would have liked to understand what I was losing in terms of performance using HTTPS as opposed to plain HTTP. Now, this sounds like a statistical model, but this is just for the size. Now, if you take the size itself, can be thought as a combination of these factors: the compression, because that's what we tried to compress with to gzip, compress the output. The coordinate precision, because we tried that as well, just to reduce. So instead of having, we're dealing with coordinate geography, excuse me, geographic coordinates, okay? So just reduce the number of digits after the decimal point and see what happens. The format of response, GeoJSON and TopoJSON. Therefore, the number of features and the number of points, because you can have few polygons, but very detailed, or very many polygons, which not much detail in them. So basically, it's just the number of polygons. Oh, by the way, with that only with polygons, okay? So with lines, points, we didn't really try. But I think polygons are the most complex feature that you can send to a browser. So, okay. So, okay, a little bit more about the factors. Of course, TopoJSON is supposed to be some faster because it reduces the size of the output. HDBS is included as a factor because, okay, we'll see it later, but I was kind of, actually I didn't think that it was a factor affecting because, I mean, after the end checking, usually the connection is kept alive because of HTTP 1.1, so it should be fast enough. That's my understanding. Okay, average response size is 10 to 100 kilobytes, just to give you an idea. We tested two data DBMSs, CouchDB and PostGIS, whatever. And of course, the number of points, that can be reduced as well. So it's not a given, because we can use generalization just to reduce the complexity of a polygon. How? OK, I think that you should be familiar with that. So this is the venerable Douglas-Packard algorithm. Basically, you simplify a line, and of course, a polygon, in a sense, is a set of lines, by just drawing successive, connecting successive points, vertices along the line, and setting a threshold. If this bit here, from this segment to this point, is less than the threshold, this point gets deleted. Okay, so this is a way to simplify polygon, so to drop points without altering too much the shape of the polygon. Now, that's fine if you have one polygon. If you have, as we had, polygons which are contiguous to each other, then the generalization in one polygon may be different from the generalization of the polygon adjacent to it. So you will end up having gaps or overlappings. You don't want to have that. So that's why we use the SE simplify preserve topology function of PostGIS. Oh, of course, all the pre-processing, spatial pre-processing was done in PostGIS. Another thing, TopoJSON. I don't know many of you are familiar with it, but basically is GeoJSON using topology, as the name may suggest. And so you can define a polygon. Oh, because in TopoJSON, every polygon is defined by itself, like an island, which means that when you have two adjacent polygons, you are actually duplicating data, replicating arcs. So if you take another view as a polygon, as a collection of arcs, you can share the same arc between adjacent polygons. Like in this case, you define a polygon as a collection of arcs. And there is a vector of arcs, so you can have another polygon, and you can reuse the same arc. So make the second polygon point to, say, this arc here. It will reduce the size. So generalization. We chose, for no particular reason, two levels of generalization, okay, based on the degrees, because we had all geographical coordinates, which are translated into 1 kilometer, roughly, and 5 kilometers, okay, at the highest level of generalization. Then we had two more levels, so more detailed levels, but I didn't use those data for these experiment. Yeah, Now, the test procedure we used. We had one intern at our university, Richard, which patiently simulated what the user does. So with Selenium, he recorded like 200-pound zoom operations. Then that was duplicated in order to have roughly 1,000 actions. Then those 1,000 actions, every action being a pan or a zoom or something, was played back using Selenium. And it was played back using different combination of factors, different database, compression yes, compression no. So that we ended up with about 17,000 different observations. Oh yeah, and of course we built OpenLayers 2, a small front end with OpenLayers 2 and a small back end with Node.js connected to CouchDB and PostGIS. Yeah. So in order to reduce the number, as much as possible, the number of the variability in our observations, we run this test nighttime or during weekends. We had a dedicated VM, with Windows VM with Firefox on it. We reduced the bandwidth to half a megabit just to test our listing environment. And of course, there was no caching on the browser, because every time my little application server sent something to the client, it said that there was no caching, so the headers. Okay, so no caching was allowed, neither on the client, neither on the server. Yeah, that's it. So we tried to reduce the noise to a bare minimum. Still, we had a bit of weird results. So different times for the same operation. Weird. So I did a little bit of cleaning. So actually, I noticed that the variance was much higher when there were more than 400 geometries returned. So I did a little bit of cleaning, and I was at 14. Yeah, I dropped 14% of points. Okay, because otherwise I wouldn't be able to do proper modeling. Despite this, results were, yeah. So this is time. Okay, the frequency of time. As you see, there is a peak here in the, say, 0.3 seconds or something. But there is still a long queue, which I didn't expect, to be honest. Size, yeah, it's kind of, it's not exactly, OK, that's supposed to be expected, because the density of geometries is different from one part of Australia to the other. Number of geometries, yeah, OK, same as this. And these are a measure of throughput, geometries per second, which is what we are interested in, finally, because we just want to put as many polygons as possible in the shortest amount of time. And this is roughly a Gaussian, which is heartening. Now, first and foremost, we wanted to use TopoJSON, but it was not supported by OpenLayers 2. By the way, now it does, but we did this work a few months ago. So I will use the model to give you an estimate on how much TopoJSON could help improve performance, okay, using the statistical model which we developed. But no real data on it. Well, I shall rewrite it using either D3 or OpenLayers 3, I think. OK. So yeah, database factor. First, we ruled out the use of CouchDB. Actually, we use CouchDB, and we're pretty happy with that, but not for this kind of stuff, because the current implementation of GeoCouch is slower than PostGIS. How much slower? Well, a fair bit, I would say. From 50% to 150%. This was done just using bounding box queries on the same data, loaded in PostGIS and in CouchDB. And yeah, we did a little bit of testing. But so From now on, we focused only on PostGIS, okay, because we found out that GeoCouch was not yet up to speed. Yeah, actually, I tried a few things to make GeoCouch work faster. So I played with list functions. I tried different views and different type of views, storing the geometry in a different way, but didn't work out. So yeah, GeoJSON versus TopoJSON. What I did is just to grab some data in GeoJSON, then to convert to TopoJSON using a command line utility. And I found out that consistently, at least for our data, basically the size reduction was dramatic. So it was reduced to 30% of the original size. So if we had some polygons, which were, say, 100 kilobytes, then you may expect that to be reduced to 30 kilobytes, which is pretty good. So for the statisticians among you, this is a standardized quantile, and you see that I made a little bit of experiment, and they are roughly Gaussian, so I'm pretty happy with these results. And so now, size model. So this is the way statisticians model the world. So I presume that size was influenced by precision. Precision means the number of digits after the decimal point. We tried with 4 and 15. 15 is a full precision. 4 is a reduced one, but still, at some zoom levels, it's still good enough because the user won't notice the difference. Precision, generalization. You remember the introduction of number of points per polygon. Plus E. E is whatever I haven't considered yet. Okay, so it's supposed to be a white noise. OK. So I'm first modeling the size, and then I will use the size to model performance. So 2 models. Now, with a little bit of a oh, yeah. Then I use size per geometry because that was more useful for modeling performance. So I'm not actually modeling size, but size per geometry. Because size, of course, it depends on the number of geometries you have. So using the analysis of variance, what we got is this effect. This is the mean effect. And so this is an effect which is the same throughout all the combination of factors. Then, if you have a precision of 4, you add 378 to 422. If you have a generalization of 001, then you add to 578, 422, this one. Okay, so you add the. If you have basically 3 things to add, and in order to have the predicted value for that particular combination of factors, like this. What is the expected size of 100 geometries with a precision of 4 at the generalization level of 001? It is 100 geometries per multiplied by what I said before. Okay, so roughly 174 kilobytes. What if I want to have a precision of 15? Well, we get a bigger size, of course. Actually, a 45% increase. So it's a predictive model, okay? Yeah. Performance model, almost done. Performance model is geometries per second. So it is it's based on factors now are, of course, size per geometry, and protocol, which is HTTP versus HTTPS, and the compression. And of course, white noise. Now, the results are interesting, but this hurt anything as well, because we found out that I use a linear model for this, not an analysis of variance, actually, but the compression is not relevant. It's far too high. That's the number over there. The protocol plays a part, and of course the size per geometry plays a part. So basically, these are predicted values. The green line HTTPS and the blue line HTTP, which means that performance in geometries per second throughput decreases when the size per geometry is increased. OK, that's kind of obvious. And HTTPS plays a part in it, which just kind of surprised me because I didn't expect that. So we are losing something when using HTTPS. I mean, we as our project. And we are losing this bit of throughput. So now I can quantify that. I can say, look, we decided to use HTTPS, fine. But remember that we are using this much, with this much in terms of performance. And another thing that is hurting a bit is that you may notice there is still a lot of variability, variance. You see here, points are very much dispersed. So I don't know what happened, to be honest. I tried to get all the factors in there, but there is still something which I haven't considered. Could be network latency, could be, I don't know, the client. I don't know, really. I tried to get rid of all possible external factors to have a controlled environment. But still, because you may notice the R square is just 0.17 for this model, which is pretty low. So yeah, performance model. So these are the predictions of this model. Basically, I'm using the size. First, I compute the size per geom. Then I use compute the throughput, okay, with the parameters. So if I have a generalization 0.05, 4 degrees precision, I will get for a 96 geometries, which is the average response size in terms of geometry of polygons, which we have from our data. You will get a time of 0.3 seconds. If you use another combination of factors, like 0.01 and 15 degrees precision, then you will get an 8 times worse performance, okay? 2.6 seconds. This gives you an idea how important these factors are. Now, last slide. Predicting the impact of TopoJSON. Same model as before. The only thing that the size per geometry, we know it is reduced by 70%. So I introduced the underlined factor there. And what I get is that it will roughly double the performance. So by using TopoJSON instead of GeoJSON, I'm expecting our system to be double as fast. This is the prediction. I hope that it will be turn out to be true. So where's the slide? OK, generalization has a positive impact, precision as well. Protocol plays a part, despite what I first thought. Compression has no impact, so it's pointless to gzip things. And database, of course, has positive impact because it's relevant because PostGIS is way faster than CouchDB, at least the current version of CouchDB. And TopoJSON is expected to give us a performance boost. And that's it. Questions? Yep.
Is are the tests available somewhere so I could test on my machine?
Yeah, sure. Actually, they are on GitHub, but there's a private repository. I'm going to make them available. Yes, sure. Test data and R scripts.
Yes, yeah.
They all lot. Okay. So yeah, sure. Other questions? OK.